So, okay. Today, first, let me recall some notions from information theory. Okay, so first of all, the definition. Information of complex manifold X is a smooth proper map smooth proper such that X is isomorphic to a fiber over a distinguished point. So here is a fiber. Over where 0 in B is a distinguished point. Distinguished point. Okay. And
What is B? Is it a curve or something?
no, this is some base. It doesn't matter what it can be non-smooth, for example. But its formation is such a map, smooth proper flat, with the property that its central fiber, a fiber over a distinct over some point that we choose, is isomorphic to our variety X. So, and now let me recall what is Kadaira-Spencer map. Spencer map. So suppose that B is smooth, or B smooth. We have the following exact sequence on X. So first of all, we always have a map from the tangent bundle to X to the pullback of a tangent bundle to B. And if we restrict this map to our variety X, what will be the kernel? Right? So it's a very geometric picture. We have a tangent bundle here. We pull back tangent bundle from base, and if we restrict this map to our fiber X, what we will obtain here will be tangent bundle to X. So we have a fiber. So if we pull back tangent bundle from base, then and here is a tangent bundle to X. In kernel, we will obtain exactly the tangent bundle to our fiber, right? Okay. Maybe for someone it will be easier to work with the dual sequence with Keller differentials and relative Keller differentials. This is just the dual sequence in the case when everything is smooth. Okay, so we have this map, and now what is this bundle? If we restrict pullback of a tangent bundle to B to the fiber X, what is this vector bundle?
Trivial.
Yes, it's trivial. Yes, this is more or less obvious. And now, what is the Kadeira-Spencer map? Kadeira-Spencer map. This is a map that we obtain from the long exact sequence of cohomologies. So TB0, that is the global sections of this vector bundle is mapped to where? From this exact sequence.
Which one of the?
And this is Kadeira-Spencer map. Okay? Now, let me recall a notion of infinitesimal deformations, because, in fact, this first cohomologies of the tangent bundle of X are parametrized by isomorphism classes of infinitesimal deformations, and then using this interpretation, I will say what is this map, what is Kadeira-Spencer map. Okay, so first of all, definition and deformation of X this is just a deformation over dual numbers. So we work over complex numbers. So this is just deformation over such a base. So this is a scheme that with point and one tangent direction, and deformation over it is so-called infinitesimal deformation. Okay, and now just statement from complex geometry. Isomorphisms classes of infinitesimal deformations of X are parametrized by the first cohomologies of its tangent bundle. Okay? And now let me give an interpretation of the Kadeira-Spencer map using this statement. Suppose we have a vector in a tangent space to the base, tangent space of base over a distinguished point. Okay? So what gives this tangent vector in terms of maps from dual numbers, from spectra of dual numbers? What is this? If I have a tangent vector.
It's a map from the spectrum.
So this gives you a map from B to B, right? And here we have our deformation pi, and we can take pullback.
This is something we should know, or how is this?
Was this?
Defined? Yeah.
Yes, this is an exercise from Hartshorn. What is the Zariski tangent map to a scheme? That if you have to have a vector in tangent space to some point is the same thing is to give morphism from dual numbers such that the unique closed point is mapped to 0 in this case.
Ah, okay, okay.
Yes,
So the
and the
vector-
tangent vector is the.
okay.
So dual numbers is a scheme. This is one closed point
Yeah,
with a
with the-
tangent direction. Okay. So if and recall that for Kadeira-Spencer we had a deformation of x over a base b, and so here we want to give some interpretation of this map. So suppose we have a tangent vector to the base over our distinguished point. So this gives you a map from dual numbers to B, and we can consider just pullback of our deformation. And this will be also a deformation of x, right? This is a deformation of x. Okay, and now Kadeira-Spencer map. Yes, and this is of course infinitesimal deformation. Right? Just because this is over dual numbers. And Kadeira-Spencer map is exactly the map that maps V here to the class of, I denoted it by xv, to the corresponding class of infinitesimal deformation, right? Because I didn't prove this because we haven't time, but there is a statement that this vector space parameterize you infinitesimal deformation. So the Kadeira-Spencer map is something that maps tangent vectors to B to the corresponding class of infinitesimal deformation. Okay, just using pullback.
And,
Okay.
Yeah, and probably pi here should be surjective also for.
Yes, but this is this was a deformation of x.
Yeah, so it's surjective, right?
Yes, we can suppose that this is surjective. It's flat, smooth, proper map. Okay, and now what next? Okay, maybe last time we discussed fine moduli spaces and coarse moduli spaces, and maybe I should say that for fine moduli spaces, why infinitesimal deformations are important? Because usually if we have a fine moduli space, some fine moduli space, and suppose that x is a point in this moduli space, so there is a fine moduli space that parameterizes some sort of objects, and x is a point in this moduli space, then infinitesimal deformations of x usually are exactly tangent space to x in this moduli space. Okay, but this is, I will not explain all this notion, just to recall for those who know this, and maybe and for those who don't know, who have never met infinitesimal deformations before, maybe some motivation why it's important to study them. Okay? So this was Kadeira-Spencer map. Yes, and now let me discuss notions of universal deformations. So first of all, if we have a deformation and if we have a map from B0 to B, and here we have a distinguished point, and that is mapped to a distinguished point of B, of course we can consider the corresponding pullback deformation. that is just x over b. Okay, and then definition, we will say that a deformation is complete if any other deformation of B is isomorphic to a pullback by some morphism. Okay?
Deformation of x?
Yes, a complete
Не-не,
deformation of X. Ладно, нормально.
нет, там просто написано
Yes. A deformation of X. Sorry. If any other deformation of X is obtained as a pullback. So if we have some deformation of X, then this is called complete if we can obtain it as a pullback from this complete deformation. Now, if this map is unique, then pi is called universal as usually. Then pi is called universal deformation. And there is a slightly weaker notion of versal deformation. So if deformation is complete and just the tangent map over distinguished point is unique, then this is called versal deformation. So what does it mean? Is that x pi b, and suppose that our deformation is obtained from two different maps from B prime to F, then we требуем. Как сказать требуем? Require, точно. Then we require that the corresponding tangent map in distinguished point coincide. So that T0 from F. Okay, so we ask uniqueness only for tangent maps. Okay, this is so-called versal deformation. And now let me formulate a difficult theorem from deformation theory, Kuranishe, I suppose. Theorem that the following theorem, that for all complex manifold, for all x there exists a versal deformation versal deformation that will be denoted by in such a way deformation of x, and its tangent space over distinguished point is isomorphic to the first cohomologous of tangent bundle of x. Okay, and now and moreover the following is true. So we
Sorry, what is def x? What is this object?
so this is a versal.
No, is it a base or total space?
This is a base deformation.
Okay.
So there exists x versal deformation. Okay, this is the base of the corresponding versal deformation. Okay, and moreover, if second cohomologous of tangent bundle to x vanish, then there exists a smooth versal deformation. A smooth versal deformation exists. So here we don't require smoothness, and in the smooth case, in fact, this is given by Kadeira-Spencer map.
We don't require smoothness of x.
No. We ask x to be smooth. I force him. Yes, we ask x to be smooth, but we don't. Я неправильно слово сказала. So here, versal deformation can be non-smooth in general. If we don't have this vanishing, then maybe there is no smooth versal deformations. Deformation. There exists some, but it's not smooth. And if we have this vanishing, then it claims that smooth versal deformation exists.
You mean the base? The base?
Yes. Smoothness of def x. Smooth versal deformation def x exists. And I recall that we that Kadeira-Spencer map we defined for smooth base. So if versal deformation is smooth, then we claim that this isomorphism come from Kadeira-Spencer map. Okay, so for since this is a deformation of x, we have the corresponding Kadeira-Spencer map from tangent bundle to first cohomologous of tangent bundle, right here. And in the case when this is smooth, I claim that this isomorphism comes from Kadeira-Spencer. So in general, Kadeira-Spencer is not isomorphism. This is some map. So there might exist some infinitesimal deformations that doesn't come from our fixed deformation. And for universal deformations, this is not true. So for versal deformations, or all infinitesimal deformations come from our versal deformation. Okay. Next, if global
Excuse me.
sections.
Question: if in the first case, when base is not smooth, Is this map canonical? Is this isomorphism canonical and given by some natural map?
Yes, this is a natural morphism, but it's not Guseva map. Okay?
It's not, but this is the same construction that you described.
But for
when we take
Guseva map, we use this exact sequence. So for there is a construction, analogous construction, but the construction that I explained, you used this exact, short exact sequence of tangent bundles. This exists only in the smooth case, because we in general case we don't have exactness exactness of this tangent exactness of this short exact sequence, okay? Of this short of this sequence.
Yes, but we have another construction with a tangent vector and spectrum of dual numbers. And
Yes.
it always gives a map from the tangent space to H1.
Yes.
Is this map or not?
But
Because I
if-
read some.
But we have problems with the risky tangent space when our distinguished point is not smooth. Yes, maybe the same construction with dual numbers gives you the map. But here we used, but to when I explained this construction, I didn't explain why infinitesimal deformations are the same as first cohomologies of tangent bundle, right? And here we should use check homology to do this. So I'm not sure, but maybe maybe I didn't think about non-smooth case. Okay. So if global sections of tangent bundle vanishes, then a universal deformation exists. Universal deformation exists, and the third, the versal deformation of X is versal for any of its fibers xb if dimension of the first cohomologies is constant. So what is written here? We have a versal deformation, and we have our x that is a fiber over distinguished point, and also we have some nearby fibers, right? And for nearby and for these fibers, we also have a deformation, right? Because so we deform X, and in particular we deform other fibers that are near X, right? And here the claim is the following: that if dimension of the first cohomologies of tangent bundles to these fibers is constant, then this deformation is also versal for these nearby fibers. Okay?
I mean, in a small neighborhood, that this dimension just equal to the distinguished point.
What?
In
No.
a s-
So I claim that here we also can consider fibers not only just over our distinguished point, but over some points B, right?
Yes.
And this is also a deformation of xb. And I claim that if this is a constant, if this dimension is constant, then the induced deformation of xb is also versal for xb.
But I'm confused about the word constant here. So it's a constant in a small neighborhood of the distinguished point, or Because it's just a number.
Yes. No.
В смысле, на каком открытом множестве это константа вопрос? Или
Ну,
нет?
нам не важно, у нас достаточно на открытом маленьком. So
In
it's
some
not
neighborhood.
just some open neighborhood, okay?
Containing the
Containing
distinguished.
Containing zero, of course.
Ah.
Our distinguished point is zero.
Okay.
Easy example where it's not locally constant.
Hmm?
Is there some easy example where this number is not locally constant? Everything is smooth. I mean,
I need
if
to, I
everything
need
is
to
smooth,
think, okay?
But if everything is smooth, it seems hard for this to not be locally constant.
It's what?
How can this thing not be locally constant if everything is smooth?
Как это может быть не локально постоянно, если...
Если все гладко.
But so we always have a upper semi-continuous for so locally it's always so maybe the claim is that if we have in a some neighborhood if it's constant in some neighborhood, then in this neighborhood all our deformation will give reversal deformations of all fibers in this neighborhood. Okay. So locally, it's always true because upper semi-continuity, but not that here we don't require def x to be smooth. So here I don't claim that this is that we have,
but locally it's
but-
smooth. It's not
so here just this is true even for non-smooth deformation, for non-smooth reversal deformation. Okay. Okay. And what next? Okay. And next, what we obtain for K3 surface. K3 surface. Corollary. That for a K3 surface S, there exists a universal deformation. Deformation where this universal deformation is smooth of dimension 20. Okay? So if we have a K3 surface, then there exists a smooth universal deformation of it. And the dimension is 20. But maybe I can leave it as an exercise because we have computed all just using Serre duality and computations of Hodge numbers that we made before, we immediately obtain this. Okay? So what you need to show is that this is 0, this is 0, and that the dimension of this space is 20, but this follows from identification of tangent bundle and first differentials on X, right? So this is an exercise. This week I will definitely send you exercises, but
No,
so what?
dual, right?
No. It's not Serre duality. This is just a canonical identification that comes from the fact that this is one-dimensional. So we just take pairing. So T.
So this is true. 3 surfaces.
Yes, this is true just for K3 surfaces, of course, because we should have a global section, non-zero global section here. And here we have a canonical global section, and that gives you identification of tangent bundle with first differentials. Okay? So in fact, this is all this is exercise. Okay? Okay. And now let us discuss. Okay. And let me prove the following statement that is more difficult for K3 surface. That in fact all smooth deformations of a K3 surfaces are K3 surfaces. Okay? So if we have a deformation of a K3 surface, X maybe B, then what I claim is that XB is isomorphic to a K3 surface. So that all fibers of a deformation of a K3 surface is still a K3 surface. Okay? What I need to show, so suppose that we have XB, a fiber over a point or some point B. So first of all, I claim that the first cohomologous of XB is 0. Why this is so?
Because Hodge numbers are constant.
It's why dimension of singular cohomology is constant in families, in deformations.
But it's
On theorems, they're all diffeomorphic.
Yes, by Ehresmann's theorem. So locally all fibers of a deformation are diffeomorphic to each other. So from the point of view of differential geometry, they are the same. So in particular, their singular cohomologies dimension of their singular cohomologies are the same. Okay, so this we obtain immediately. And the problem is with the canonical class. So we need to show that canonical bundle is trivial. Okay? This is the problem. So first of all, if we take a self-intersection of the canonical bundle with itself, then it will be 0. I didn't. So an explanation that I have in mind is that we can consider Hilbert polynomial of the relative canonical class of X if we restrict the corresponding relative canonical class to a fiber, we obtain a canonical bundle of a fiber. So we see that Hilbert polynomial of canonical bundles of fibers is a constant, just because Hilbert polynomial in flat families, it's constant, right? And this is the top degree of a Hilbert polynomial. This is self-intersection of canonical bundle. Maybe you know some simpler explanation. I don't know.
Does it work in non-projective case?
Yes, I think so.
polynomials defined on theory.
But we can I need to think. Okay, but I think that the self-intersection of canonical bundle will definitely still be will depend smoothly on the base. It doesn't matter whether we work in a complex, in a purely complex setting or in algebraic setting. So I think that this will be true in any, but an explanation with Hilbert polynomial doesn't work. I need to think how to do this in complex setting. Okay. So what we obtain from this? We obtain from this that Euler characteristic of trivial bundle is equal to 2 for all points on B. Just because we always have Noether formula, right? That tells you of topological characteristic. Right? This is a Noether. We have already discussed it. Noether formula. So we know that this is 0, and we know that this is constant, right? So we obtain that Euler characteristic of trivial bundle is equal to 2, right? What next? Okay. From this, we obtain that second cohomologous should be equal to 1 from this. Because we have already shown that the first cohomologies are vanishing, and we know that the global sections are equal to 1. So we know that the second cohomologous is one-dimensional, and by shear duality, we know that this is equal to global sections of canonical bundle. Shear duality, right?
Wait, how to deduce the characteristic is true?
Just from Noether formula, because we know that this is 0, and X topological is constant. What is topological error characteristic for a K3 surface? Okay, so here we use shear duality, and from this, so we know that there is a global section of canonical class. So to prove that canonical bundle is trivial, it is enough to show that there is a global section of dual line bundle. Okay. And now, yes, and we have already discussed this. This will follow from upper semi-continuous
Continuity.
So let me recall classical statement that I cannot relate. So the following function is upper semi-continuous. Upper semi. So what is mean? That is the set such that global sections is greater or equal to some fixed number is closed in B for all here R and M. Okay? So what we obtain from this? So we know that self-intersection of canonical bundle is 0. So from Riemann-Roch theorem, we obtain that 2 is equal to Euler characteristic of canonical bundle. So, and this is less or equal to and this is from Serre duality. XP plus Euler characteristic. And from Serre duality, this second cohomology is equal to the dimension of global sections of canonical bundle twisted by canonical bundle. Okay, so
Why do we have inequalities in the second proof?
here, but here it doesn't matter. So this we obtain from Riemann-Roch in the fact that the self-intersection of anti-canonical bundle is equal to 0. So here by definition of Euler characteristic, and here from Serre duality. Okay. Serre duality. And and from this we immediately obtain that yes, and now what we know? We know that over our distinguished point over 0, x0 is K3 surface. So we know that this is trivial line bundle. So we know that its global section is equal to 1, right? So, and 1 is definitely less or equal to 1. So from semi-canti, ну вы поняли. This inequality works for all points for all B in a neighborhood of 0. So from this we obtain that should be greater or equal to 1. In this. So we obtain that here is this is trivial. Okay?
Можно тут написать? А
Что?
почему сама точка Б не могла попасть в замкнутое множество, где уже подскочила размерность?
В смысле, нет, в значит, обратное утверждение к полунепрерывности в том, что вот в открытой окрестности точки, в которой это уже выполняется, будет выполняться. То есть это просто, то, как я сформулировала полунепрерывность, это в другую сторону. Там говорилось про замкнутое множество. Меньше либо равно замкнутое, больше либо равно открытое. Окей.
Да.
So So, okay, so we proved that a canonical bundle of all fibers in a neighborhood of 0 is trivial, and so we obtain the statement that deformations of K3 surfaces are still K3 surfaces. Okay? Хорошо. And now I want to explain something about local period map. Local period map. So suppose yes, suppose we have a deformation of a K3 surface S over smooth B. Last time we discussed local systems. Fine. Local system this local system. And last time we have proved that if we consider the corresponding vector bundle, then we can embed the second relative differentials and it such that fiber-wise we will obtain an embedding of two zero part in the second cohomologies of in the complexified second cohomologies of fibers. Окей? Вот Егор гораздо лучше меня это все знает, наверное. Okay, and now, so we always have such an embedding. In fact, even for even if we deform not K3 surface but some smooth complex variety, we have such an embedding, but this will be not a line bundle. This will be some sub-bundle. Okay, but we need this picture for, we will use this picture only for K3 surfaces. So we have such an embedding, and if we assume B for B simply connected, this local system will be what for a simply connected base? Для односвязанных пространств про локальные системы что можно сказать? Yes, they all are trivial, so we have a canonical isomorphism with the following constant local system, right? And so only for simply connected base we have this canonical isomorphism. And so for simply connected B, we can define the period map. how we will do this. So first of all, we will fix so-called marking. We discussed this last time, but I didn't say this word. Fix marking on S, and this is a canonical identification. Or this is not canonical. This is just an identification of its second cohomologies with the lattice that is 2 copies of E8 with U. Okay, so we should fix this canonical identification of lattices, and this is called marking. We will next time we will discuss that in fact. So for all K3 surface, just an abstract one, we cannot have any moduli space. I will explain more precisely why we cannot parameterize K3 surface. But surprisingly, for marking K3 surfaces, there exists a fine moduli space. It will not be Hausdorff. It's a very strange moduli space, but this is a fine moduli space. Okay? So if we fix a marking, then we will have something. Then we will be able to parameterize K3 surfaces. And also next time we will discuss why for polarized K3 surface we have coarse moduli space. So for marking K3 surfaces there is a fine moduli space, and for polarized there is a coarse moduli space. Okay, so we will see different examples of moduli spaces. Okay, so so we fix this isomorphism, and with this assumption, we obtain canonical markings for all fibers. XP Z, using just the fact that for simply connected we have this canonical isomorphism. This is canonically isomorphic to the second cohomologies of S, and this is canonically isomorphic to lattice. And so, because for a non-simply connected base, we don't have canonical identification, right? We have some identification, but we cannot glue them smoothly over our base. And for simply connected, we have this canonical identification. Okay? The period map this is the induced map from base to a projectivization of the complexified lattice that maps B to its image of to zero part. Okay? So we have discussed last time that we have an embedding of a line bundle into a vector bundle that corresponds to this local system that exactly that fiber-wise gives you an embedding of 2 zero part into complexified cohomologies of fibers, and now but not that if our base is not simply connected, then this line subbundle gives you an embedding in the complexified second cohomology. And here we want a point from a projective space with fixed lattice. So we should have some canonical isomorphism of the second cohomology with this lattice. Without this, we cannot define a period map. We will discuss next time what this is so-called local period map, and next time we will define what is a global period map for a non-simply connected base. But here we definitely use that B should be simply connected because we want this canonical identification. Okay? So using this canonical identification, we have a line bundle, and line bundle will give you an embedding just using universal property of projective space into the corresponding projective space. Okay? Понятно? Или не очень? Окно открыто надо. Okay. So one more time. Before we had a when we discussed this line bundle fiber-wise, we had an embedding right? But this is not canonically but there is no canonical identification of this complex space with this complex space. So this line bundle that was given by relative canonical differentials abstractly cannot give you a map to projective space just because we cannot canonically identify this with this complex space. But if we have a simply connected base, then this identification is canonical, okay? So we obtain a map to projective space, okay? Okay. And what next? Yes, and I don't. Okay. Yes, and here I need to. Yes, here I need to explain what is a Griffith's transversality. So we have this map, and we have discussed last time that this is holomorphic map with values in period domain.
Wait, what is? What is?
Why it's holomorphic?
No, what is? There
So-
is
so-
Strange symbol there.
Это is a holomorphic map. Is a holomorphic map with values in period domain. So we discussed last time that in this projective space we have a 20-dimensional smooth period domain. That is an open subset inside a smooth quadric.
Projectivization, so it's 19 dimensional.
No. The period domain is 20-dimensional. Okay. So we have a period map with values in period domain, and now I need to explain something about Griffith's transversality.
The light is 22-dimensional, right?
So
But in version 21, you use a quadric.
this is this is an open subset inside quadric. So quadric is 20-dimensional, just because the corresponding projectivization is 21. Окей, все. Это мы последний раз обсуждали. Griffith's transversality. for this this particular case of K3 surface. So Griffith's transversality. We tells you something about differential in a distinguished point of this map from base to projective space. That tells you that if you take what we have here, we have a map, and we want Griffith's transversality will describe you differential of this map in distinguished point. So this is a map from tangent space to B to tangent space of the corresponding projective space. What is the tangent space to projective space?
V factored by the line.
Homomorphisms from. So this is a map.
To lambda modulo rho of.
So generally, this is a map, right? This is a homomorphisms from O-1 to V factor O-1. Okay? So I formulated in such a way because, in fact, Griffith's transversality works in a more general setting of variation of Hodge structures, and more generally, H20 part isn't one-dimensional subbundle. So more generally, here we have a Grassmannian. And for Grassmannian, tangent bundle is tautological homomorphisms from tautological bundles to quotient bundles. Okay, Griffith's transversality gives you a precise description of the corresponding differential. So we should obtain something that will lies inside homomorphisms of 2-0 part inside modulo 2-0 part. So here I just write down what is this tangent space to projective space in our case, because here tautological subbundle corresponds to 0-2 part, right? The corresponding vector space is canonically identified with complexified second cohomologies, and we should factor it over 2-0 part, right? This is exactly what is written there, but in our case, O-1 is 2-0 part of the the corresponding K3 surface, right? So here, of course, in this factor there exists this subvector space, because if a factor, in this quotient, if we take a quotient of second cohomologies by 2-0 part, there is 1 part inside, right? So what tells you Griffith transversality? That the corresponding map factors through the following composition. So here is a Kadeira-Spencer map, okay? So we discussed Kadeira-Spencer map. Griffith's transversality tells you that first we should take Kadeira-Spencer map. Here I will explain in a minute what is this map. And here we have an obvious embedding, okay? So Griffith's transversality is a statement about differential that tells you that your differential of this period map is some composition of Kadeira-Spencer map alpha that I will explain in a minute, and an obvious embedding. Okay? So let me explain what is the corresponding alpha. So yes, we should obtain something from 0 to r to h11 r. So let me recall that this is what? This is the first cohomologous. And suppose that we have a, and this is the global sections. So suppose we have an element here, then we have already discussed that there is a canonical identification of tangent space with first differentials just using a non-zero, any non-zero element. Ой. So we map T. Oh, тут не было. So we just take a convolution of a two form with the corresponding tangent space and obtain something from first differentials, right? Okay, and how we define this map? So if we take so in the case of K3 surface, this map gives you just canonical identification of, right? So we identify, so if we fix an element from global sections of second differentials, then we have identification of tangent bundle with cotangent bundle, right? If they are isomorphic, then their first cohomologies are also isomorphic. And this is exactly this map. Okay, so we fix an element here. And from an element here, we obtain a homomorphism from first cohomologies of tangent bundle to the first cohomologies of cotangent bundle. Okay? Very simple linear algebra. And not very simple, and in fact very difficult Griffith's transversality tells you that your differential of period map is this composition. Kader Spencer, then this easy map alpha, and then we embed it into this homomorphism. Okay? And this is in fact much more general statement, but for K3 surfaces, it's very easy to formulate just because here is something one-dimensional, and this is something very easy. Okay. And
transversality. What is the intuition about transversality?
Ну, потому что это что-то говорит про трансверсальность вариации структуры Ходжи. Но я сейчас не хочу это.
Okay.
Абсолютно. Так. So this was Griffith's transversality, and now I think I can formulate local, so-called local theorem. So we have already discussed that for a K3 surface there exists a universal deformation. And in fact, I will explain in a minute. We can think of, we can take just consider the universal deformation as an open, some open small disk in 20-dimensional complex space. So in fact, this universal deformation is something simply connected. If universal deformation is something simply connected, then we can define the corresponding universal period map. That is a map from deformations of S to period domain. And now I claim that this is a local isomorphism. Okay? So what we have here? We have already discussed that proof. That deformation of S is smooth and we can suppose that this is something simply connected. And we know that period domain, not factorized, just period domain, is also something smooth, 20-dimensional. So we can, and also this is simply connected. This is in fact small disk. Okay, and what we know? We know that our dimension of first cohomologies is 20, yes? Because we have discussed that if we deform K3 surface, we obtain a K3 surface, so this dimension is constant. So we obtain that this is a universal deformation for all fibers of S. Okay, in fact, to prove that this is a local isomorphism, it's enough to prove that its differential in the distinguished point is bijective. And to prove this, I will just use Griffith's transversality. So it is enough to show the differential is bijection. And here we can use Griffith's transversality. What Griffith's transversality tells you? That TB0 by the Kodaira-Spencer map is isomorphic to first cohomologies of tangent bundle, just because this is a universal deformation. And we have already discussed that when deformation is versal, it's not even universal, then we have this isomorphism. And we have already discussed that if this universal deformation is smooth, then this isomorphism is given by Kodaira-Spencer map, right? So here in Griffith's transversality, we have an isomorphism for a universal deformation, right? And we have already discussed that in case of K3 surface, this is also an isomorphism, right? And we have already discussed that this is that this is bijection. Okay, so we from Griffith's transversality, we immediately, and this difficult Kuranishi statement about deformation theory, we immediately obtain that the corresponding period map for universal deformation of K3 surface is bijective. Okay? Все.
Why is it enough to show the differential is bijective?
Just because, so here we have two 20-dimensional smooth varieties. So to prove that this is a local isomorphism, and also we have, and also we know that deformation, that this universal deformation induces universal deformation of all nearby cycles. So to prove that this is a local isomorphism is enough to prove that the corresponding differential is bijective in zero. So this is a local isomorphism.
Local isomorphism here is analytic.
Yes. And okay, next time we will explain. We will discuss what we have for merged K3 surface and for polarized K3 surface. Just because this is a very interesting examples of fine moduli spaces and coarse moduli spaces. Okay, and then maybe we will discuss subjectivity of the global period map. But before we also need to define what is global period map. Все.